Okay, everybody. So, what we're going to be up to today. Listen up, everybody. Today we're going to be going over specifically average rate of change and instantaneous rate of change in detail, and looking at how problems of those caliber work. We're also, everybody, going to revisit the idea of particle motion. Okay, so position, acceleration, velocity, that sort of thing. Your homework tonight is just doing one of those problems fully. Okay, and next week we're going to do an AP question involving particle motion. Okay, if you're on the fourth form expedition, Jake, we'll make that up later. And Robert?
And people who are going to do Jim Wilcox.
Jim Wilcox is a counselor. That's next weekend.
So we don't have class?
So, no. We have class. It's just
No, we can't.
those two. If you're going to the fourth form, we'll talk later about what you need to make up. Okay?
I'm not going to be here to respect.
All right. So, basically, let's revisit two notions. Okay? Today we're going to talk about rates of change. Okay? Okay. And there are two rates of change we're chiefly interested in. Okay. Do you remember what they are, Lyndall?
There is an instantaneous rate of change.
Uh-huh.
And
Average.
there is a, what Faulkner said.
What'd you say?
Average rate.
Average rate of change. Okay. So there's average rate of change.
Makes the dream work.
Okay. And instantaneous rate of change. Instantaneous rate of change. Okay? Now, average rate of change, we'll abbreviate that ARC often. Okay? The average rate of change, by the way, okay, it is essentially the average rate, average rate of change, it's the way a system changes over amount of time, which will correspond to a what? The slope of a
Line.
not tangent line, but a secant line. Good. So average rate of change is basically traditional slope dash the traditional difference quotient. Difference quotient. Okay? And it's the same thing as basically the slope of a secant line.
I think this is filming what you're writing.
Yeah, no, backwards. It flips it.
Flips back?
Yeah.
Okay.
I know, it's weird.
Science.
Okay. Slope of a secant line. Instantaneous rate of change, okay, is abbreviated IRC. And what does it represent?
That's a point, right?
It's at a point, so it's the change at a specific point. So it's modeled after the tangent line or the derivative. Okay? So instantaneous rate of change is the derivative.
Michelle, is that traditional slope divided by the difference quotient? Or?
No, it's traditional slope or the difference quotient. Okay. But instantaneous rate of change is the derivative or slope of a tangent line.
Mr. Dowell,
Uh-huh.
see where you put the little dot in the parentheses? It's like
Oh,
a
frowny face, yes.
Yes.
Okay. Yeah, I guess it looks like that. Okay, so slope of a tangent line, all right? Any questions about what these things represent? They're fairly straightforward, right? Okay. Let's actually take a look at some word problems in which we're going to be using average rate of change and instantaneous rate of change, okay? Because both of these are, both of these basically are when we start to use this calculus, this derivative calculus, in a real-world setting, okay? So let's start off with a word problem. This is one I did for the earlier class, and I'll reproduce it up here for you all, okay? So a population of parrots.
What type of thing?
We'll make them monk parrots. I'll tell you about monk parrots later, okay? A population of parrots, okay? Basically, a population of 500 parrots, excuse me.
500.
Yes. 500 parrots is released a forest. Okay? Okay. The population grows, or population changes according to the following equation. And that equation is going to be P of t equals 500 times 1 plus 4t over 50 plus t squared. Okay? Where t is the time in years. Okay? So, at year 0, there'll be 500 parents. Okay? So on and so forth. Okay? Now, so this is typically what one of these problems will look like at first. Okay? And then what will happen is we'll ask questions about this system. That is what's happening with our parents and what's happening over time. This one.
Is it 50 t squared?
No, plus t squared.
Did we do a little bit of this last year?
We looked at something very similar to this last year,
Equation
yes.
looks really similar.
Because I like parents. Yes.
What is? Can you just replace P with F?
You can if you want to. Okay. Yeah.
What
Yes.
What is that under? Is that 50 t?
That's 50 plus t squared. Here, maybe it'll help if I do it this way. Okay.
Where's Backer?
Dude, it's so much quieter.
He's out of town.
Is that what?
He's out of town.
He's out of town.
Backer?
Yes.
Yes.
All right, guys, focus. Okay. 4t plus, is that better?
Yes,
Yes.
T squared, okay. Where t is the time in years, okay? So, oftentimes when you have one of these questions, you're going to be asked to do, guys in the back, hush, okay? You'll be asked to do multiple different things. So for example, over here, we had, I did this problem earlier. We have the question, how many parents are there after 5 years? Okay? Well, is that actually using any calculus whatsoever?
No.
No. All I have to do for that is just evaluate this thing, this equation, at 5. Okay? And doing so, I end up getting that there are 633.3 parents. Question, can I have a third of a parent?
No.
Well, you
You
can,
gotta go one
but
up. You gotta go one
it
up.
wouldn't be a very, very happy parent. Actually, you don't go 1 up. Okay?
Go down.
You round just like you would any normal situation. So 633 and 1/3 parents in this situation is just going to round down to 633 parents. Okay? So how many parents were there after 3 years? Or 5 years, excuse me? 633 parents.
You have more than that.
No.
But not a whole more. Okay? We still treat the average, we still treat this with the regular rules of rounding. Okay? Typically speaking in these problems, okay, whenever you're doing involving some sort of animal, like a parrot or a dog or a cat, or a person, like a human, you can't have, or a large finished good, like a car, okay, or a house. You can't have partial numbers there, because that doesn't make any sense, okay? You can't have half a person. You can't have a quarter of a cat. You can't have, 2/3 of a car, okay? So so when you have those, you just round accordingly in these problems, okay? So if it's, and again, follow the same rules of rounding you're used to. If I have half a person, I round up. If I have less than half a person, I round down, okay? Likewise, things which you can have partial numbers on, kind of unfinished goods, okay? Food items, so like pizzas or cakes or things like that. You can have half a pizza, you can have a quarter of a cake. Or things which can be naturally subdivided, okay? So for example, I can have half a gallon of something, okay? I can have a quarter of a bushel, okay? Things like that. So when you're measuring these things out, it's okay for those to be partial. It's not okay for things like people to be partial, okay? So keep that in mind. So, we ended up getting 633.3 parents, which we round down to 633 parents. That's how many parents we had after 5 years, okay? Huh? Okay. So, another question you might get involved in this might have to do with the change in the population over those 5 years. Again, that's not going to be a calculus question, that's just going to be a question of, well, how many parrots did we start with, and how many did we end with? Well, we started with 500 parrots, we ended with 633 parrots, so what was the change in parrots over 5 years? 133 parrots, okay? Where this thing would become a calculus question, or starts to hit into calculus, is if we asked, over those 5 years, what was the change in the population, okay? So not a simple, how many parrots did we start with, how many parrots did we end with, but sort of, during time, basically for any given year, what was my rate of change in parrots, okay, or average rate of change. So the rate of change over the 5 years for the parrots is basically modeled after slope. You take the population after 5 years, subtract from the initial population, and then divide it by the change in time, okay? And if we did that, we discovered that over 5 years, the average rate of change of the parrots was 26.6 parrots per year, okay? So that's what 133 divided by 5 gives us, basically, okay? So that's the example. You're going to always use average rate of change if the word over appears in your problem, or if I'm giving two numbers for my time, okay? So the rate of change in population from time A to time B, or over a duration of time, or things like that, okay? Those are always signs I'm going to do an average rate of change, okay? Instantaneous rate of change, though, that one's going to be a bit different. Anytime you're going to do instantaneous rate of change, you will be given a single point to do it at, okay? So you'll be told, what is the change in parrots, or what's the rate of change in parrots, at 5 years, or at 6 years, or something like that. So let's go ahead and do that as an example, okay? So the question will be something like, what is the change in parrots, or the change in the population, at 5 years, okay? So because I'm given 1 point here, 5, okay, I'm going to treat this as an instantaneous rate of change. Okay, so I'm going to basically take the derivative of the equation above. Okay, so P of t is given. We want P prime of t. Okay, now really that 500, does it do anything?
Nope.
No, it stays out in front as a constant.
Wait, why do you want the derivative? Why don't you just put... never mind.
Okay. Why do I want the derivative? Because I'm looking for an instantaneous rate of change.
Okay.
Okay? And that's what the derivative models. Okay? So starts off with 500. Now we come into our fraction, or to our parentheses. It's 1 plus 4t over 50 plus t squared. Any special rule here?
Not for the one.
Not for the 1, it's just derivative constant, which is
0.
0. And for the fraction, I have to use the what rule?
Quotient.
Quotient rule. So low-D high minus high-D low over low squared. Anyway, 50 plus t squared times 4 minus 4t times the derivative of the bottom, which is derivative of 50 plus t squared? 2t. All over 50 plus t squared squared. Okay. Yeah.
What do you mean, like, at 5 years? I don't get how that implies the instantaneous rate of change.
Okay.
I
So
get it's at a point.
at a point.
The change in population, wouldn't that just be 133?
No. So, okay. Let me. And maybe I should put the word rate. What is the rate of change in population at 5 years? That might make it a little clearer. Typically speaking,
The rate of change, that makes
Yeah.
sense.
what is the rate of change in the population at 5 years? Is that better?
Yes.
Okay, there we go. So that will clear up the confusion. Keep in mind that you might see it written the way I have it written up there. And the way I know they're talking about an instantaneous rate of change here is because they only gave me 1 point in time at 5 years. If they said something like they gave me 2 points, or if they used the word over the 5 years, then I know we're talking about a duration of time.
Okay.
Okay? Is that better? Okay, so this is what comes out to be. Okay, so I go ahead and I now evaluate this at 5 because that's what I'm. Excuse me. That's the year in question. I want to know the instantaneous rate of change in. Okay, so p prime of 5. 500 times 0 is 0. So we can just ignore that part. So it'd be 500 times this thing evaluated at 5. So it's going to be 50 plus 5 squared, which is 25, times 4, minus 4 times 5, which is 20, 2 times 5, which is 10, all over 50 plus 25 squared. Okay, which is 50 plus 25 is 75, so we'll just make that 75 squared. Okay?
Nice.
At this point here, should I keep going like by hand?
Nah.
Nope. At this point here, whip out one of these guys. That's what they're for. Okay? If we go ahead and do this math here, 500, okay, times all this in here cleaned up, we end up getting an instantaneous rate of change of 8.8 repeating parrots per year. Now, okay, when talking about a rate of change, is it okay to have partial numbers?
Nah.
Yeah, actually, in this case, it's okay to have partial numbers because I'm not talking about actual number of parrots. I'm talking about the rate at which they're changing, and so in this case, it's okay to have a partial number. Now, I can't actually have it. It's either going to be 8 parrots this year or 9 parrots this year. Okay, 8.8 would imply it should be more like 9 parrots this particular year, but that change in rate that they're going at is 8.8 parrots per year. So it's okay for your rate of change for things like parrots or people to be a fraction or a decimal. Okay, it's not okay for your finished number, for the actual legit number to be that. Yes.
Is that why you put like 26.6?
Yep, that's why it's 26.6. I also said about 27, so I would say about 9 here as well. Those are also acceptable to say. Okay, but the actual rate of change there is 8.8 parrots per year. Okay, so look at the difference though. The average rate of change for my 5 years suggested that the number of parrots per year we changed was 26.6 parrots. But at year 5, my change in parrots is only 8.8. So what does that mean is happening?
It's decreasing.
It's decreasing. The rate at which my parrots, the growth rate for parrots is going down.
Going extinct.
Okay? Not going extinct. I have more parrots than I did before. It's just that it's leveling off. This could be for many reasons. One, the forest in question could be reaching its carrying capacity for parrots. Okay? 500 parrots were able to multiply and increase in size, but once you hit a certain number of parrots, the growth level might level off because, quite simply, the forest can't support any more parrots. Okay? That's one reason this could be happening. Could be other reasons as well, like maybe initially in the first couple of years, nothing was preying upon the parrots because these were introduced to this forest. But now the local forest critters have discovered parrots are tasty, and so now are, picking the parrots off, and that slows down the growth rate. Okay? Yeah?
How do you create an equation for something like this?
How do you? Typically, what they do is they just study the system and see. They actually go backwards a lot of times before these. So instead of using the equation to predict the growth of the system, they look at the growth of the system to write the equation. Does that make sense? All right, and we're actually going to learn that later this year. Okay, we could do that if we have things like the acceleration, or if we have an equation that governs the acceleration, or equation that governs velocity, or the rate of change equation. We can use that to figure out the population equation. Okay, later on. The only thing we'd be missing is a starting point. That is how many we started with. Okay, that the question can't tell you. Okay, but here we can get our growth equations. So this is how a rate of change equation works, and you could do this sort of rate of change for any sort of system. Okay, that works this way. So let's take a look at another example. Okay, go ahead and pull it from the book here. actually I pulled that one from the book, but I changed it because the original question had to do with bacteria per hour growing in petri dish, and that's boring. Parrots are much more interesting.
What kind of parrots were those again?
Oh, I said at the beginning that if we had to call them, we'd call them monk parrots. I chose monk parrots because there's a real world example that gets used a lot. In New York City back in the 50s, like a population of monk parakeets or bower parrots was being smuggled in the city. The guys smuggling them in were caught, and instead of taking the parrots to a zoo or sending them back to where they're from or euthanizing them, the parrots were all just sort of, no one knows exactly who did it or the circumstances of it, but basically the smuggled parrots were just released upon the docks into the city. So, all of a sudden, prior to this, New York had no parrots, wild parrots, and now they had a bunch of wild parrots flying around. Authorities figured, well, these are tropical birds. This is New York City. It's cold in winter. They're probably just going to die out. So we'll just let nature take its course because it's too hard to try to round them all up. Well, nature finds a way, and the parrots ended up surviving. And so you can go to New York City now, and there are wild monk parrots living in New York City. So there are populations of these parrots, and they're kind of a nuisance because they make these giant nests that and they'll make them in places where, like on light fixtures or like traffic lights or things like that. So it's kind of a pain in the butt.
What do they look like?
Oh, they're just little parrots, little like green parrots, parakeets. Yeah, and they just fly wild in New York City.
Good for the monk parrots.
Yep. So there was for a long time they tried to eradicate them because they were a nuisance. They were causing damage to buildings and things. Now they've learned, since it's just too hard to get rid of these parrots, so they instead of trying to get rid of them, they just try to manage the population. So they encourage the birds to build their nests in certain locations, so that way the birds can build their nests and be happy and not causing damage to things.
Is that one right there?
No, that's a regular like bush dairy.
You a parrot enthusiast, Mr. Dowell?
I do like parrots, but I watched this really sad a Nova documentary about the parrot trade and about people keeping parrots. And ever since I watched that, I've decided that no one should really own pet parrots. I mean, it was like really, really sad.
You can go get a New York one.
That's true. I could get a wild one in New York and just have it be my friend. But
I think Cotton would eat it.
Cotton doesn't seem that interested in birds. My other cat Bilbo would try to eat it, but Cotton doesn't seem all that.
RT might eat it.
Who?
RT.
All right. Here's an example. Oh, my son? No.
Yeah.
He right now doesn't even know his hands are attached to his body. So, I mean, but we all started off that way. It takes a while to figure out things like your hands or your feet or things like that. In fact, I touched his little nose yesterday, and that totally he was like, whoa! It's just like, I have this thing on my face. Where did this come from? It's amazing. Anyway, let's look at an example here. This is a geometry problem that's been adapted to calculus, which is what happens a lot, okay? And we've got the volume, okay, so volume, okay? And we're told the radius, okay,
Is this another rate of change problem?
yeah, of a right circular cone, a circular cylinder, right? Yes. Is given by the equation square root of t plus 2, okay? And its height by 1/2 root t, okay?
What is a right circular cylinder?
Like a Coke can.
What's a left circular cylinder?
Oh, that's not right as in right angled, so like perpendicular. Yeah. Where t is seconds. Okay. And dimensions are in inches. Okay. Cubic centimeters, or dimensions are in centimeters. I'm saying that because inches is stupid. Okay. What we want is we want the rate of change in volume with respect to time. Okay? Well, we're going to see problems like this at the end of next week. They're going to be a lot more involved. Okay? Because what we'll end up doing is we'll find a way how we can model both the radius and the height separately. Here they've been modeled for you, and so you're given equations for both the radius and the height with respect to time. Okay? So, first question I have for you is, we're trying to figure out the volume of this cylinder. Okay? How do I find the volume of a cylinder? What's the equation for that?
Pi r squared times the height.
Pi r squared times the h. Okay, remember a cylinder, so it's the basically area of the circular base times its height. Okay, so pi r squared h, r is t plus 2, and h is 1/2 root t. So volume is going to be equal to pi times root t plus 2 squared, okay, times 1/2 root t. I can clean this up, can't I?
Oh yeah.
Volume is going to become, what's this going to become?
T pi
Just t plus 2, right? So it's pi, or t pi, or pi t plus 2 pi times 1/2 root t, okay? That's how it's going to come out to be, all right? Now, we want the change in volume. So what that means is we're going to take volume here, okay? And we're going to take the derivative of it, okay? So we're going to do the derivative of volume with respect to time, okay? That's what dv by dt means there, okay? So, what rule am I going to use to take the derivative here?
Product rule.
Product rule. Product rule says keep the first one the same, so it's pi t plus 2 pi, times the derivative of the second one. I could rewrite that as t to the 1/2, right?
Yeah.
So it's 1/2 times 1/2, or 1/4 t to the negative 1/2, okay? Plus, keep the second one the same, and multiply it by the derivative of the first one. What's the derivative of pi t plus 2 pi?
Pi.
Just pi, okay? Just pi, good. And so this equation here tells me the rate of change of the volume with respect to time. So how quickly the volume is changing, okay? If I wanted to, if I actually were given a time, I could plug that in and find the actual change in volumes at specific times. But that would be the instantaneous rate of change of the volume. Would I want to do that if I was trying to find the average rate of change in volume? No. I would just take my volume equation and use it at 2 different times, with the change in time on the bottom being the other variable, okay? But you see how this works? You can use any equation or any system and treat it like calculus this way. Yes, Lobo?
Calculus.
Never mind? Okay, you're good?
I think, yeah.
Think you're good? Alright. Alright, any questions here?
Oh, sorry.
Nope.
I found a question.
Finally got the question. Okay.
Alright. So from the volume equations, just like some algebra question. Whenever you multiply the pi times the root t plus 2, wouldn't the pi go outside the square root?
It would, but what I do here, I'm taking root t plus 2 and I'm squaring it.
So it would cancel out.
So those would cancel, and that leaves me pi times t plus 2.
Oh, so you cancel out the root before you multiply.
Yes. Yeah, because remember PEMDAS, parentheses, then exponents. So I can't do anything with the parentheses inside, so I'd move the exponents, which is squared. That cancels the square root out. Okay. Then I move to multiplication, okay? Multiply that pi through, okay? But that's how we get this right here, okay?
Yes, sir.
All right, good. We're going to shift gears now. We're going to talk about, in the last 12 minutes of class here, we're going to talk about position questions. And this is what the homework tonight's going to be about, okay? It's going to be about questions involving particle position, particle motion, okay? So, particle motion. Okay? In calculus, okay, these are common questions because they're very easy to demonstrate kind of the notions of what we're after here. Plus, they have real-world applications. We always describe things as being as moving as a particle, but you can, particle is just a word for something that moves in this case. Okay, I'd be looking out the window and watch a human walk from point A to point B and use these same equations to describe that. I could be looking at traffic on a highway and watch a car go back and forth or something, and use these equations to model it. Okay, it's just a way to model a system I'm looking at. Okay, now real-world systems are much more complex, and what these particle motion questions do is they boil it down to just simply how far to the left we move and how far to the right we move. So I guess for you all, right and left. Okay, but with particle motion, one thing that's always clear with them is we always we've got three things going on. We have a position equation, okay, usually written as x of t, okay. Its derivative is going to be velocity. Okay? And velocity, again, is the derivative of the position. It's also too written as v of t. Okay? Now, when we do the derivative of velocity,
So its derivative is velocity.
yes, the derivative of position is velocity. And now we're doing the derivative of velocity, which is acceleration. Okay? And that's represented by either x double prime of t, the second derivative of x, or the derivative of velocity, or its own equation a of t. Okay? Yes?
Is there a reason you're using t?
With respect to time.
Okay.
Okay? Yeah. Typically with these real-world physics questions, everything is with respect to time as opposed to respect to x. And it's simply because time is the common variable in which everything's changing by. Okay? Which is nice. Okay? But these end up being the three things we're looking at. Okay? All right. Oh. Now, there are some things to note when you ask these questions tonight, okay? One thing you'll be asked about is whether I'm moving to the left or to the right. Motion to the right, okay, would be positive velocity. Motion to the left would be negative velocity, okay? So, if velocity is positive, means moving right. Negative means moving left. Okay? So if I have positive velocity, I'm moving more towards the right. If I have negative velocity, I'm moving more towards the left. Okay? With acceleration, okay, acceleration could also be positive or negative. Positive acceleration, okay, means I'm not speeding up. I don't want to use the word speeding up or slowing down because speed is going to be basically both looking at your velocity and acceleration together. Okay, but acceleration might be energy towards the right would be positive and energy towards the left. So if I could be having a negative velocity, so I could be moving towards the left, but my acceleration could be now to the right. And so what's going to happen is I'm going to start slowing down, aren't I?
I remember this one.
Okay, and eventually stop and then start moving in the opposite direction. Okay, so positive acceleration is basically, I'm going to describe it as motion or energy to to the left, or to the right, excuse me. And negative would be energy to the left. And this is probably not the right word to use, but I'm no physicist, so I'm going to use what is easy for me to describe. Okay. All right. Yep. Good. And so, when their signs agree,
What's
you speed up.
If they're both positive.
both velocity and acceleration?
Okay. Yeah. So if my velocity is positive and my acceleration is positive, that means I'm speeding up in the rightwards direction. If they're both negative, that means I'm speeding up in the leftwards direction. Okay? If they're different, when signs are different, okay, you slow down. Okay? So again, if my velocity, for example, is positive, if I'm moving to the right here, okay, but my acceleration is to the left, I'm going to slow down, and eventually I'm going to stop moving right and start moving left, unless my acceleration also changes, okay? So keep that in mind. All right, any questions about these kind of little nuances in velocity and acceleration? I'll give you a second to copy things down, okay, before we move on to talking about nuances with position.
It's a pain.
Why is this a pain? This
So dumb.
It's not dumb. It's actual real world stuff at this point. Yeah.
That's what I've been.
Really quick. I didn't really see the
1 second. I mean, we're almost done with class. So.
I didn't really see the answers to this. What derivative of this?
So
Real mature,
The
Jim.
derivative of that is just pi.
Trying to go to the bathroom.
That's
It's
the
4
pi.
minutes
So
left.
it's just zero. Yep. Pi.
Oh, yeah.
yeah, remember
Mind
too,
out of the
this is
gutter,
going to be a
Jim.
product rule. So
Oh.
it's keep first one the same, derivative of the second one, and then add to it derivative of the first one, keeping the second one the same. So you just took the derivative of both the first and the second separately. Okay, so with this one, I'd be timesing it by the second one kept the same, and then add that derivative times that. Does that make sense?
I think so.
Okay, good. All right. Position now, okay? It's nuances, okay? Again, basically position is going to be, if my position is negative, that means left to the origin. Positive means right to the origin. So positive is steps away to the right of the origin. Okay. Negative steps to the left. Okay. The other big thing with position is your often will be asked for a total distance traveled. Okay. Now, total distance traveled is going to be basically the sum of how far to the left and how far to the right I've moved in various ways. Okay. Basically, it's an absolute measurement. Okay. So, total distance traveled
If you just do the absolute value.
is the sum of the absolute value of the distances between time points. Okay? What do I mean by that? Okay? For example, maybe in my first second I moved 3 spaces to the right. Okay? So my total distance traveled would be 3 there. Okay? In my next second though, I move 2 to the right. Okay? So that'd be 3 plus 2 or 5. In my third second, I might move 4 back. Okay? Well, even though I'm only 1 space away from the origin, my total distance traveled was 3 plus 2 plus 4. Okay? So in that case, 9 units traveled. Does that make sense?
Is that distance between the points?
Between points, time points. Time points. Okay? Just as I described it there. If I drew it up here, it would be much more clear. So it would be like, here's my origin. Okay? Here's 1, 2, 3, 4, 5. So in the first second, I move 2 spaces. Okay. In my second I move to 4 spaces. So my total distance traveled there is 4. In my third second, I move back 3 spaces. Okay, well that's still 1, 2, 3, 4, 5, 6, 7 spaces. Okay, so my total distance traveled would be 7 units there. Does everyone see that? Even though my distance away from the origin is only 1 at the end. Okay, make sense now? All right. Homework tonight's going to be a part of a motion problem like this. Okay, I will see you tomorrow in class.